Good morning, good afternoon, good evening. Thank you for joining us today for this is our fourth CAN-based webinar this year. I'm Rick Rockershausen from Grid Connect, and I'm joined today by Torsten, and I didn't ask you how to properly say your last name, but I'm going to say it, Gedenk, from Emotas in Germany. You can correct me when I turn it over. Torsten will be leading our webinar today on CAN higher layer protocols, CANopen, J1939, and UDS. Emotas specializes in higher layer protocol stacks based on CAN, and including the ones covered today. So first of all, thank you, Torsten, for joining us on the North American time zone to host the webinar. I know you have lots of knowledge to share on this topic. So I'm anxious to get started. If you could just advance to slide 1, I want to cover a few logistics before we go. If during the webinar you have questions, please click on the Q&A button on the bottom. We will have people monitoring the questions submitted. And if it's a question we can type the answer to during the webinar, we will do that. If it's a question that we can't answer by typing, or it's too long or complicated, we'll save it to the end. You know, we're talking about a lot of protocols, and we can get quite deep in some areas, might not have time to cover all that. We will try to cover all of your questions after the webinar if we can't get to them all today. And also, we are making a recording of this webinar that we will share out with everyone at the end. And again, thanks everyone for joining. I'm going to turn it over to Torsten now.
Okay, thank you very much. And welcome from me. Well, my name is Torsten Gedenk, and I'm work for Emotas in Germany, and I'm dealing with CAN for more than 20 years. And in particular, I am dealing with CANopen, J1939, and also UDS. And today I'd like to explain something about these protocols. At the beginning, well, I hope that most of you know at least a bit about CAN, but I will say something about CAN to start with. And basically, I'd like to answer the question why we need additional protocols on top of CAN. So, well, basically, CAN bus is a connection of multiple nodes or multiple ECUs on a 2-wire bus cable. The 2 wires on CAN are called CAN high and CAN low, and the differential voltage between the two wires is used to transmit ones and zeros. If you connect the scope to the CAN wires, to CAN high and CAN low, you might see something like that, ones and zeros. And these ones and zeros together are CAN messages which are sent between the CAN nodes. Well, at both ends of the CAN bus, you should have a termination resistor to reduce the reflection on the wires. But yeah, let's go on with the CAN messages. Basically, a CAN message consists of multiple components, but the most important parts of a CAN message is the arbitration field with the CAN identifier and the data field. The arbitration field includes either an 11-bit or 29-bit CAN ID or CAN identifier. And in the data field, one can put up to 8 bytes of data. All the fields around just make sure that the CAN ID and the data are transmitted correctly. Well, I could explain more about that. I could even talk for 2 hours about CAN. But for now, it's just important to know that CAN messages have an 11 or 29-bit CAN identifier and can contain up to 8 bytes of data. Well, I am aware that there is CANFD, which is the successor of CAN. And CANFD supports much higher bit rates and longer frames. I know that it exists, but today the topic is CAN, classical CAN, and the protocols on top of CAN. Yeah, well, if we look at the slide here, it's a screenshot of one of our tools, and at the top you can see CAN messages with CAN identifiers and just some data. And at the bottom you can see an interpretation of these CAN messages, in that case according to the J1939 protocol. So if you just look at the CAN identifier and at the CAN data, you don't know what it is. You need, in that case, you need to know that it is J1939, and then you can see signals and the values of the signals. So basically, that's why we need protocols on top of CAN to have rules how to interpret the bytes or how to send the signals and parameters via CAN. Yeah. I can just, or the CAN specification or CAN standard just defines that there are CAN identifiers which may have up to 8 bytes of data. And they can make sure that these identifiers and data are transmitted in a secure way on the CAN bus. But the CAN specification does not define the meaning and the content of the CAN messages. It just, there is CAN and you can use it how you want to use it. Well, so yeah, but if you want that your devices are able to communicate with each other, you need to agree on rules or on protocols on top of CAN. And so we need protocols to define how a signal, for example, a temperature or voltage or parameters or even firmwares are transmitted or on CAN. For example, you could do a firmware download on CAN, and the firmware of an ECU might be 0.5 megabyte or 4 megabyte long. And in order to transmit such large data, you need rules or transport protocols to transport that, such data on CAN. Well, there are lots of different CAN-based protocols. I'm just taking a list from Wikipedia at the bottom. I don't want to, or I can't explain them all, but today we speak about CANopen, ISO-TP, J1939, and UDS. Yeah, and let's just start with the first of these protocols. CANopen is a protocol which is developed and maintained by the organization Canon Automation, which is headquartered in Germany, but the organization has about 700 member companies at the moment. And the first release of CANopen was already in 1995. So it's nothing new, but it's a rather mature and stable protocol. There at the moment, or a few days ago, there had been approximately 1,510 CANopen vendor IDs. A CANopen vendor ID is a number which identifies a CANopen manufacturer of CANopen devices in a unique way. So each manufacturer has to get a CANopen vendor ID. So we can assume that there are or had been at least 1,500 companies developing or selling CANopen devices. In reality, it might be much more because not also each manufacturer is supposed to get its own vendor ID, but not everyone that does so. The CANopen protocol originates in factory automation, but now it is used in almost all industries, as I will show you on the next slide. And well, CANopen itself provides a huge set of services, including services, for example, for firmware download or something like that. I mentioned that CANopen is used in multiple industries and it originates in factory automation. So, and also in embedded machine control. But nowadays, it's used in almost all industries, which are shown here. There are medical devices with CANopen, elevator control, or even special purpose cars. You might wonder what a special purpose car is. For example, in Germany, the police cars have a blue light on the top, and the blue light controller communicates using CANopen with the vehicle. So that's a special purpose cars. So you can say, or one can say, that CANopen is used in multiple industries. Yeah. And now let's look into the technical details of how CANopen works. This gray box here shall be a CANopen device. A CANopen device in CANopen has a so-called node ID, or a device is a node in CANopen, and nodes have a node ID between 1 and 127. Of course, your device might have an application, and well, the application might work fine without CANopen. For example, if you think of a battery, batteries exist for decades and they work fine without CANopen. But maybe now your customer comes and tells you, I like your battery, but I want to read the voltage via CANopen, for example. And in that case, you have to add CANopen communication services and the so-called object dictionary into the firmware of your application. Basically, the object dictionary is a huge list of signals, parameters, or data in CANopen called objects, which can be read or written via CANopen. So all information from your application which you want to read or write via CANopen needs to be located in the object dictionary. There will be an additional slide about that later on. And in order to transfer or to send or receive the values of this object, there are different communication services. A few of them or some of them can be used to exchange data or objects, and other communication services can be used to control the devices or to do additional tasks maybe. Well, if we continue with the example of a battery, I have another slide for that. Now we assume the application is a battery which can communicate via CANopen, and the battery has a voltage, maybe 13 volts here. Well, in CANopen, there are so-called device profiles, and the device profile is specific for a class of devices. For example, there are device profiles for batteries, for motor controllers, for medical devices, for chargers, and so on. And there's one device profile with the number 418, which define batteries. And inside this device profile, there's the definition that the battery voltage is stored at the object 6040 subindex 0. And I'll be going to explain the details later on. It's a 30-bit wide object, so 4 bytes. It's read-only, it means you can only read it. And the voltage is stored, and it's not exactly millivolts, but almost. And so these 13 volts internally will be represented as this hexadecimal value. Well, and if you want to read, or if another device want to read out the voltage, it could use the so-called SDO service. The SDO service is a service in CANopen to read or write the values of specific objects. And the first CAN message here is a request sent from some device. And here it includes the object number, the index and subindex, which shall be read. And the response below also includes the index. And here we can find the value of this object, which is the same, which is written here. So I will explain these communication services in detail later on, but there are services to read or to write a value of an object. But maybe you want to configure your battery that it cyclically sends out the voltage, so you don't have to request it each time. You just tell the battery, just send out your voltage or temperature, whatever, every second. And also these communication services exist in CANopen. It's called PDOs, or process data object. And here we have an example where one CAN message contains the battery voltage and something else, maybe a temperature, I don't know. That's the basic device model. And if we look at this slide, again, the gray boxes are CANopen devices. And if multiple CANopen devices communicate with each other on the application layer, they exchange CANopen objects. A CANopen object could be a single bit, or a byte, or 4 byte, or 20 bytes, or half a megabyte, whatever. But on the application layer, they exchange such objects. Of course, if you have an object which is longer than 8 bytes, it will not fit into a single CAN frame. So CANopen and other higher layer protocols define rules how to split an object, for example, into multiple CAN frames with a CAN identifier and data. And on the receiver side, it will be put together again and forwarded to the application. So on the application layer, we are exchanging CANopen objects. On the CAN data link layer, obviously the devices send and receive CAN frames with a CAN identifier and data in it. And if you look at the physical layer, at the wire, you can see different voltage levels, which represent zeros and ones, basically. The CANopen object dictionary is, as I said, one of the most important parts of a CANopen device, and the object dictionary includes the list of all signals or parameters which you can read or write or send. And each object has an address, and they have a 16-bit address and the so-called 8-bit subindex. So basically all objects in a CANopen object dictionary are addressed by an 16-bit index and an 8-bit subindex. And the device profile standardizes, for example, that the battery voltage is always at the object 6040 subindex 0. And for other types of devices, there exists similar device profiles. The basic idea is if you exchange devices from different manufacturers, but if they follow the same profile, you can continue to use them. Let's have another look at the object dictionary. Well, as I have mentioned, the index is a 16-bit value. We have a range between 0 and FF at the end. But the most important parts of the object dictionary are the yellow ones in the middle. And today I will focus on the yellow ones in the middle. Why I could talk for 8 hours about CANopen, but today I only have approximately 20 minutes for this protocol, so I need to focus on something. And basically, the yellow ones are the most important parts of the object dictionary. And the range between 6000 and 9FFF is for objects which are defined in the standardized device profile. So, for example, our battery voltage was located in this area. But if you develop devices which does not fit or which are not specified in a device profile, or if you just develop manufacturer-specific devices, or if you even follow a profile but want to add something manufacturer-specific, there are thousands of objects in the manufacturer-specific segment, and you could put your manufacturer-specific information into this part of the object dictionary. And finally, there is the communication profile segment. And there are a lot of objects which CANopen requires for themselves in order to configure the communication behavior of the device. A few slides ago, I had mentioned that one can, for example, tell the battery that it shall send its voltage every second. And there are objects to configure the communication behavior in the communication profile segment. The objects itself have the different attributes. And an object in CANopen can either be a variable, an array, a record, or a domain. A variable in CANopen is just like in the programming language C, a single variable. An array is are multiple elements with the same data type. And a record in CANopen is similar like a struct in the programming language C. So are multiple elements with different data types. And finally, there are domain objects, and the domain is just a large unstructured piece of data. So for example, if you want to do a firmware download via CANopen and send 0.5 megabyte of a new firmware to a device, the object which would receive this firmware would be a domain object. Additionally, the variables and the member of the arrays and records may have different data types, unsigned data types, signed data types, floating point data types, a lot of predefined data types. Additionally, the access of the objects, or there's an access type. So dumb objects can be read-only. A few of them can be write-only. You may have constant object, like for example, a serial number, and objects which you can read or write. And additionally, the CANopen specification define which objects are mandatory, which means you have to implement them. Fortunately, there are only 3 mandatory objects, so you could develop a minimum CANopen device which only includes 3 objects. You could say that it is a CANopen device, nothing more, but it would be a CANopen device. And you have a lot of optional objects or conditionals, or when in certain conditions you have to implement them. And objects have additional attributes. We had the example of the battery voltage, and the CANopen or Canon automation specification of 418 for batteries tells us that the voltage is located at this index and subindex 0. It's just a variable. Data type is unsigned 32. It's a read-only object, so you can only read it, and the value range is the complete data type, and the unit is something like that. On the next slide, there's just a list of other objects. Oh, where's the next slide? Here's the next slide. There are thousands of optional objects. I don't show them all, just one slide with a few of them. So the communication segment starts at object 1000. The device type is an object which identifies the type of the device. Just to show you that there are multiple object codes, different data types. You can also have strings and read-only objects, something like that. Well, I have mentioned a couple of objects, and now let's have a look how one can read or write these objects in CANopen. In CANopen, there are multiple communication services, and one of the most important ones is the so-called SDO service, means service data object, and using SDOs, you can read or write specific objects. There are multiple transfer modes for SDOs, and I start with the easiest one, the expedited transfer. Usually, or no, always, an SDO transfer is initiated by an SDO client, and the device which the data is sent to or read from is the SDO server. The client is usually a master or a controller or a configuration tool, and the other devices are just the devices in the network. In order to send an SDO message, well, the CAN ID is always 600 hex plus the node ID of this device, and we have 8 bytes of data. First byte is used for protocol information. In that case, it tells us that we want to write something. Then the index is specified, the subindex, and up to 4 bytes of data. Here's an example below. Here we are writing to the index 1017, subindex 0, and a specific value to it. The device, the SDO server, will receive this message, and it will check if, for example, the object is writable, and if yes, it will prepare a response and send it back. And the responses always use the CAN ID 580 hex plus the node ID of this device. In the first byte, there are some protocol-specific information. In our example here, the 60 means that it had been written successfully. Then the index is repeated and the subindex as well. And we have four reserved bytes because the SDO messages always have to contain 8 bytes. It's a similar example here. Basically, we want to write one object, subindex, and the 5000, which are represented here. And well, yeah, and the response, as I mentioned before, is always 580. The CAN ID of the response is always 580 plus the node ID of this device. So we have that here in this example. 60 here tells us it had been written successfully. Index and subindex are repeated. So in SDO, download writes a value of an object to a device, and it's always confirmed. And yeah, we can also read objects from a device. Reading from a device, it's called upload in CANopen. And again, the SDO client initiates the transfer. CAN ID is the same, 600 plus the node ID of this device. In the first byte, it would be different, indicating that we want to read something. The index and the subindex is sent to the device, and the device will respond, send back. Again, CAN ID of 580 hex plus the node ID of this device. At the beginning, there's a protocol byte telling us that it had been successful. Index and subindex are repeated, and we can have up to 4 bytes of data. So basically, with the SDO expedited transfer, we can read or write objects which are not longer than 4 bytes. So we are limited to 4 bytes of payload here. It might seem a bit small, but most objects are not longer than 4 bytes. But if we want to read or write longer objects, we have to use the so-called segmented transfer. And here's another example showing an SDO segmented transfer. Again, it is initiated by an SDO client, which can be a master or configuration tool. Again, we use the same CAN ID, 600 plus the node ID of this device. And in the first byte, it's a bit different here. We indicate now that we want to use a segmented transfer. The index and subindex are transferred, and in the end, the size of the object. This example here only transfers 7 bytes. This device will receive that, and it will send back a response using the same CAN ID. And then, after it has confirmed that it is able to receive the data, the SDO client will start sending these special CAN messages. And at the first byte, we have some protocol information, and after that, 7 bytes of payload, like shown here. And then each CAN message will be confirmed. In this example, that's it, because we only had 7 bytes. But if the object would be longer than 7 bytes, the sequence of request and response would be repeated until the complete object would be transferred. And here's just an example of a CAN logging of a little longer segmented transfer of 20 bytes. You can see here the first 7 bytes being transferred, and it's confirmed. The next 7 bytes confirmed, and the last 6 bytes, and it's confirmed in the end. So basically, you're using SDOs. You can read or write all objects in the object dictionary according their access rights. But an SDO transfer is always a one-to-one communication. So one device, usually a master or configuration tool, initiates the transfer, and the other device will respond. So it's only one-to-one. But if you want to want that, for example, your device or your battery, as we had this example before, sends automatically, for example, the voltage every 1 second, for example, you will need a different communication service. In that case, you would want to use PDOs. PDOs in CANopen means process data object, and PDOs are used to send multiple objects in one CAN message as a producer-consumer communication model. It means one device is a PDO producer. It sends out the values of the objects. And it does not care if 0 or 1 or many receive it. It's just it's an unconfirmed service. PDO will be sent, and the PDO may contain multiple application objects. Well, a PDO is a CAN message, and a CAN message may only contain up to 8 bytes. So we can only put as many objects in it until we have reached 8 bytes. And there's the example from the beginning. And here we have one object, the voltage, and that might be a temperature, for example. And yeah, one producer sends a PDO in 0 or many consumer may receive this PDO if they are interested in this information, or in particular, if someone has configured the devices that they listen to the other PDOs. When I do the 8-hour CANopen training, I tell the participants that it will get a bit complicated now, and so we won't get into details here. But PDO linking is the definition of cross communication between one PDO producer and one and many PDO consumers. Basically, there are objects to configure the communication parameters, for example, the CAN identifiers and some cycle rate to send a message, both on the producer and on the consumer side. And additionally, there are objects which define the content of the PDOs, both on the producer and on the consumer side. But this is a very bit more difficult topic, and if you like to learn more about that, I would recommend our longer CANopen training courses. But I'd like to go on, and I'd like to mention some other important CANopen services. Well, SDO and PDO could be used to send objects around, and there are additional services using the CAN ID 0. We have network management commands. So a master can send commands to start, stop, or reset devices. We have a special service called sync, which can be used to synchronize PDO transmissions or synchronize anything you want to synchronize. Additionally, CANopen provides so-called emergency message. That means that each device may report alarms, errors, or warnings when they happen. And finally, CANopen devices send so-called heartbeat messages, and the heartbeat message is a cyclic message of a device, and they indicate the state of the device. So a heartbeat message says, I'm still there and I'm fine, or I'm still there and I need configuration, for example. Yeah, and that has been CANopen in a very few number of slides. But, well, time is limited, so we go on to the next protocol, and if there are questions, I will try, or I will answer them at the end. Oh, next protocol is J1939. It's another protocol based on CAN, obviously. J1939 had been developed by the Society of Automotive Engineers here in the US, or in the US. Its first release was in the year 2000, so it's a bit newer than CANopen. And J1939 uses 250 kilobits and 500 kilobits as a bit rate for the CAN bus. And there are approximately, or when I had prepared the slide, there had been 1,230 manufacturer IDs. And a manufacturer ID in J1939 is something similar like the CANopen vendor ID. Each manufacturer of J1939 devices needs its unique manufacturer ID. So we can assume that there are at least 1,230 companies developing J1939 devices. J1939 originates in heavy-duty truck vehicles or any bigger commercial vehicles, could be agricultural vehicles or something like that. So big vehicles, basically. And also J1939 provides a huge set of services. There are also services for firmware download and dynamic address handling. But what's special about J1939, there is a detailed definition of thousands of signals and parameters. So each signal or parameter you might imagine which may occur in a commercial vehicle, for example, engine coolant temperature, there's a definition for that, how that can be transmitted on a CAN bus using J1939. J1939 always uses the 29-bit CAN identifier. CANopen mostly uses 11-bit CAN identifier, but with J1939 we have a 29-bit CAN identifier, which is sent at the beginning of each CAN message, obviously. The 29-bit CAN ID, where we have a 3-bit priority at the beginning, which we ignore here. And then we have an 18-bit parameter group number. But in fact, the first 2 bits are the extended database and database bit, but these 2 bits are always 0 in J1939. So yeah, it is an 18-bit number, but in J1939 we only use the 16-bit for the parameter group number. Other protocols like these or that one may use these bits with a 1, but in J1939 it's always 0. And at the in the lower byte or in the lower 8-bit of each CAN identifier, there's the source address. So each time a device sends a CAN message, its source address will be included in the lower 8-bit of the CAN identifier. And there's an address range starting at 0 up to 293. And the parameter group number identifies a parameter group, and the parameter group is a set of signals which belong together, basically. So each parameter group has a parameter group number, and inside of a parameter group we have multiple signals which are called SPNs, suspect parameter, in J1939, and they define also a repetition rate, which means how often this parameter group shall be sent. They define a priority and an inhibit time. Inhibit time is something like that. If you have a parameter group which shall be sent on change, you can define that it shall be sent on change, but not faster than 10 milliseconds. So that 10 milliseconds would be an inhibit time here. And there are thousands of parameter groups defined in J1939, and each parameter group consists of multiple signals. This is just one example of one PGN, which is called wheel speed information, and obviously it contains some information about the multiple wheels on a vehicle. The PGN has a number, that one. It defines a priority, a length of 8 byte. And well, most PGNs have a length of 8 byte because 8 byte conveniently fit into a CAN message, which also have a maximum of 8 bytes. And there's a transmit rate or cycle rate. So it means this PGN shall be sent every 100 milliseconds. And for other PGNs, the definition of these values would be different. And this PGN, for example, contains 6 signals or 6 suspect parameters. At the beginning, there's the speed of the front axle, and there's the relative speed of left or right wheels. I'm not an expert in wheels, but I have been told that if a large vehicle turns around a curve, the right or the left wheel might have the different speeds. Anyway, it's just an example that you can have, or that there are multiple signals which are called suspect parameter numbers in one PGN. And each SPN or each suspect parameter, well, they have a name. a length, a resolution, and a physical unit, maybe an offset and a value range. And I think it will be more clear if I continue on the next slide. Let's here have an example of one suspect parameter number, and this example is the SPN 110. It's the engine coolant temperature. It's just a single byte, and one bit is 1 degree Celsius. We have an offset of -40 degrees, and so the value range between -40 and 210 degrees Celsius. And each time you see this PGN on a canvas, you can be sure that the first byte of this CAN message is the engine coolant temperature, and it shall be interpreted in that way. And such definitions for such signals are defined by J1939 for thousands of different signals. So J1939 has a very detailed definition of how the signals look like and how they shall be transferred. Well, I had mentioned that ECUs or devices in J1939 have addresses. So we have an 8-bit address. So the address range for valid addresses is between 0 and 253. At the beginning, there are some so-called preferred addresses, which I will show on the next slide. It means that if you have a specific device, it shall use this address if possible. And we have an address range which is available for all other ECUs. It's important to understand that 255 means broadcast, which is sent to all devices. Yeah. And here on the next slide, I have just an example of the preferred addresses, and there are more, obviously. And for example, if you're developing a passenger operator for climate control, your device should use the source address 25, basically. And there are more. And if you develop a device which does not fit into the list of the preferred addresses, you can use any other in the range between 128 and 253. And you might ask what happens if multiple devices choose the same address. Well, there will be something, but in order to explain that, I need to explain the J1939 name. Each ECU or each J1939 device has a 64-bit J1939 name. And the name consists of 10 different parts, so to say. The most important one is the manufacturer code, which identifies the manufacturer of the device. And we have an identity number, which is the serial number. And there are some information about the function of the device and the industry group where it can be used. Anyway, the manufacturer of the device needs to make sure that the name is unique in the network at least, but if every device manufacturer does it in the right way, it should be unique for all J1939 devices. Well, and if multiple ECUs want to use the same source address, then the name is interpreted as an 8-byte unsigned numerical value, and then the lower number gets the source address which it wants, and the other have to pick another address. Well, basically, if a device starts in J1939, it sends a so-called address claiming message, and it sends the address claiming message with the source address it wants to use. And if no one objects after 250 milliseconds, the device may start to transmit all the PGNs it normally transmit, and it may use the source address. If there's another device which also wants the same source address, then the address claiming procedure starts, and in the end, the devices with the higher priority will get the source address which they want to use, and the other devices have to pick another source address. But don't worry, in the end, all devices will get the source address because there is we have 253 possible addresses. Well, yeah. Another topic is we have most PGNs fit into 8 bytes, but there are some PGNs in J1939, or yeah, some, which exceed 8 bytes, or which are longer than 8 bytes. And we also have proprietary PGNs, which can be used for proprietary or manufacturer-specific data, and they may also be longer than 8 bytes. Well, if you have PGNs which are longer than 8 bytes, you will need transport protocols in order to send them. Well, CANopen has SDOs, and J1939 has two own transport protocols. The first one, the easier one, is called broadcast announcement message. And here we want to, as an example, we want to transmit the vehicle identification number, which is this PGN. And here in our example, the vehicle identification number has 17 bytes and it's terminated by the star sign. So there are strings in J1939 which are terminated by this character, but it doesn't matter, just an example here. And using the broadcast announcement message, PGN can be broadcast to all ECUs. The PGN, which is longer than 8 bytes, can be sent as broadcast to all ECUs in the network. If the other devices receive it, or if they are interested in it, it's not defined. It's just a single ECU will send out, for example, this PGN. And in order to send this PGN, which is an example here, we need 2 other PGNs for the communication and for the data transfer. There's one broadcast announcement message which announces that 18 bytes will be sent. These are hexadecimal numbers, so it's 18 bytes. We'll need 3 CAN messages for that, and we want to transfer this PGN. And then the sender sends 3 data messages. They use these PGNs to send the data. In the first byte, we have a sequence number which starts at 0 and counts up. And in the remaining 7 bytes, we have the payload. And unused bytes are filled with FF. So using a broadcast announcement message, an ECU can send all PGN which is longer than 8 bytes as broadcast to all other devices, but it will not be informed if someone has received that. If you want to make sure that your PGN is received by the other side, you need to use a different transport protocol. There's another one called CMDT, Connection Mode Data Transfer. And it's a point-to-point, a one-to-one connection with or transfer between 2 ECUs. And in this example below, we again want to send the same PGN, the vehicle identification number, and the device which starts the transfer sends a request to send message using this PGN. And the 12 again means 18 bytes, 3 CAN messages. And the 2 here means that it can handle or can send 2 CAN messages or 2 data messages, one after another. And here the PGN is specified which shall be sent. If the other device is fine with that, it sends a so-called clear to send message. It sends, okay, you can send me 2 CAN frames. Start with the first one. And we are talking about this PGN. After that, the originator sends 2 data PGNs with a counter in the beginning, and the remaining 7 bytes are payload. Previously, the devices have agreed on sending only 2 CAN messages. So the receiver again acknowledges that and sends a clear to send message again. It tells here, okay, you could send 2 CAN frames, but continue with CAN message 3. And don't forget, we are talking about this PGN number here. And the originator sends the third data message with the remaining bytes, and the unused bytes are these. And at the end, the receiver will send an end of message acknowledge. It will confirm that it has received 18 bytes, 3 CAN frames, and we had been talking about this PGN. So using CMDT, both sides or both ECUs will know that this specific PGN had been successfully transferred from one side to the other. Yeah. And that had been the most important parts of J1939. Well, I could talk for 4 hours about the topic, but not today. Today it's time to continue. And now actually, and the next topic is UDS or UDS on CAN. Well, what's UDS? UDS means Unified Diagnostic Services, and it's defined in an ISO standard, and it's used for diagnostic purposes. And UDS itself can be used on different communication networks. So you can use UDS itself on Ethernet, LAN, and CAN. But today the topic is CAN, or higher layer protocols based on CAN. That's why we'll talk about UDS on CAN today. UDS on CAN today UDS on CAN uses ISO-TP as transport protocol. Well, CANopen has SDOs, J1939 has a broadcast announcement message and CMDT, and UDS uses another transport protocol called ISO-TP. And ISO-TP can be used to transfer up to 4 kilobytes of data. And ISO-TP itself is standardized in another ISO specification. In order to understand that, I have 2 slides for ISO-TP. ISO-TP defines a way to transfer up to 4 kilobytes. The CAN identifiers aren't defined by ISO-TP exactly, but higher layer protocols, for example, J1939 could define them. So you could use ISO-TP or UDS in a J1939 network. I've also seen ISO-TP or UDS in a CANopen network. So the CAN identifiers are not defined by ISO-TP, but by the network around the device where it is used. ISO-TP has 2 addressing mechanisms. One is called normal addressing. That means that only the CAN identifier is used to address a device. And there is something called extended addressing. And using the extended addressing, the CAN identifier and the first byte of the CAN message is used to address a device. And if you want to transfer larger data, there are 4 frame types in ISO-TP. Here we have some examples for that. For example, there is a so-called single frame. A single frame, well, it can transfer up to 7 bytes. Even if you can use ISO-TP to transfer longer frames, sometimes you have to just a shorter message. In that case, you could use a single frame. Single frames are identified by the 0 in the beginning here, and then the remaining 7 bytes would be payload. But if you have data which are longer than 7 bytes here, you need at first the so-called first frame. The one identifies the first frame. This is the length information here. It's 25 bytes. And here the payload already starts. But the receiver will send a so-called flow control message saying, yes, okay, you can continue with your data. And this 10 hex, or actually 16, means that the sender can now send 16 CAN messages. And the additional messages which contain the remaining payload are called consecutive frames and ISO-TP. In the beginning, there's a 2, and the lower part of the byte is a counter. And here in this example, 25 bytes of payload are transferred by ISO-TP. ISO-TP is just a transport protocol. It does not care what's the payload. But for UDS and CAN, we have UDS embedded in ISO-TP frames, basically. Here the red or slightly red parts is the CAN identifier and the first byte. So we have here the address, and we use in this example extended addressing is used, both the CAN identifier and the first byte. Then the gray parts of that CAN messages here are the ISO-TP parts. For example, we have a single frame here, a first frame, a flow control, and a consecutive frame. And the blue one are the UDS data. And if you would use UDS on LIN or UDS on Ethernet, the blue data would look exactly the same. But here we are using UDS on CAN, and we use ISO-TP. So if you have a CAN message, only these parts here are the UDS data. And now let's finally talk about UDS. At the end, we have UDS contains of several diagnostic services, and there are services to read or write information from a device, and read identifier, write identifier services to read diagnostic trouble codes, to download firmware, something like that. I'm saying running out of time actually. Basic message structure is there's a request response mechanism. At the beginning there we have a service ID and something like that. I'd just like to look at one service 21 hex is read data by identifier, which allows us to read one or multiple identifiers. The identifiers in UDS are a 16-bit value, yes, 2 bytes. That means we could have 65,000 different identifiers, but only 200 of them are predefined by UDS. The others are manufacturer specific. So in general, one can say with J1939, a lot of data is specified in detail, and with UDS, a lot of is manufacturer specific. And here, last slide is a sequence of UDS services. It starts in this example with reading some version numbers. Then there are diagnostic control services to change different diagnostic sessions. UDS also provides security services to access or to restrict the access to something. And we have ways to disable the transmit messages. And in this example, a programming session is entered, though, and as the name suggests, the programming session can be used to program a device. And there are commands, for example, a write data by identifier, and here a fingerprint is written, so you can know which repair shop has erased the memory and downloaded the new firmware. And this is the beginning of a typical UDS sequence. And I'd like to thank you for paying attention to my presentation. And if there are remaining questions, I will try to answer them now.
Yeah, we still have quite a few people with us, so appreciate you staying till the end, even if you were only interested in the first protocol. So I assume maybe you have some questions here at the end. Torsten's colleague Alexander has been answering a bunch that have been coming in through the Q&A, the written Q&A. I think we've answered them all at this point. So does anyone else have additional questions? Do we have a more comprehensive webinar for UDS? Well, we don't have a webinar planned for UDS. And I don't know, Torsten, do you do a UDS training?
We can do, but not a free webinar, but I have about 2 hours of training slides about UDS, but we don't have planned, we haven't planned a free webinar about that. Yeah,
if you are interested in a more in-depth training on any of these topics, please reach out to Grid Connect or to Emotas to schedule a training. We are also planning to host some open training. So you can do a private training for your company. But we can also, we will try to host a few open trainings that you can sign up and attend. There would be a fee for those open trainings to the ones that are 8 hours or 4 hours long. There would be a fee associated with that.
There's a question about the
go ahead.
And in fact, DeviceNet was the first protocol I started working with 20 years ago, and but I have forgotten most about it. But I think it uses 11-bit identifiers. Does it?
I think so. Yes.
Yeah, so it could probably coexist with J1939. Yes.
You just have to make sure the CAN IDs don't overlap.
Yeah. Yeah, but this is the general answer. If you make sure that the CAN IDs do not collide, you can mix multiple protocols. But in fact, it's easy to mix CANopen and J1939 because J1939, at least on classical, can always use 29-bit identifiers, and CANopen nearly always uses 11-bit identifiers.
So someone asking about Device Designer and the Device Explorer tools. These are tools that Emotas provides. I'm not sure if they're asking if there's a webinar or a recording of how to use those tools somewhere.
I would ask them to send me an email. We have some recordings, not a webinar, but we have some recordings, at least for the device designer, but it's not a topic for here at the moment, I think. Yeah, what the longer J1939 session. Yeah, we could do one if there are multiple interested in it. We could arrange one next year, probably. Yeah.
Yeah. Yeah, we could do maybe a slightly longer, but still within a 1 hour webinar format training on that. Yeah, J1939 is getting more and more acceptance, and it's a popular protocol these days.
Well, I don't know about all devices, but we see increasing sales both for CANopen and J1939. Yeah.
Right.
Fine so far. There's another question. What is that? Mixed protocols overlapping on the physical layer. Yeah, basically, you have to make sure that all protocols use the same bit rate. Yeah, on the CAN layer. That's what you have to.
I think Jason was helping out as well, saying, yeah, you have to be aware of your bus load.
Yeah, of course, at the end.
So thanks, Jason, for helping us answer the Q&A. There's another one about higher priority for CANopen over J1939.
If you mix them on the bus, I assume, that's a good question. Yeah, they will have a higher priority, yes, but yeah, if you mix them, you have to have some disadvantages. But at least if you keep the bus load at the lower level, it should be fine. Yes.
There's a question about Komatsu machines. What protocol they use? I think there's an attendee from Komatsu on the webinar.
Yeah, was one. Yes.
Yeah, if they know. I don't know offhand.
I don't know. I can't tell. No.
There's still quite a lot of folks staying with us, so maybe there's some more questions out there.
CANFD and CAN 2.0 cannot coexist on the same bus because old classical CAN devices cannot coexist with CANFD. No, can't be done.
Manesh has a question on how to get pricing on the tools. If you're in the US or North America, please reach out to Grid Connect. We'd be happy to help you. Otherwise, you can work through Torsten to find a distributor in your area or go directly with them. The question is, I've always heard bus load should be under 40% to avoid priority inversion.
Good question. Yeah, below 40% is always good. But what I've heard or learned from experiences, if you have a mostly cyclic transmission, so if you basically know in advance which messages will be sent when, you can go up to 80% of bus load. But if you have mostly an event triggered CAN bus, you should stay below 50%. But yeah.
these are rules of thumb.
Yeah, basically that.
Yeah.
Of course, if you have a lot of high priority messages, there will be problems. Yeah, so don't send too many messages, basically. Yeah.
Yes, Goran answered the question. Komatsu drills use J1939 and CANopen protocols. So I think the answer is it depends.
Yeah, it's always a good answer. Depends, yes.
Well, with no further questions, I think we can wrap this up. Once again, thank you for joining us. You will be getting an email shortly with the recording of the webinar, as well as the Q&A, written Q&A. And please join us next year for more interesting webinars. We hope to continue doing CAN webinars and more with Torsten and offering some training. So just stay tuned for that information. Have a great rest of your week, and thanks again for joining. Bye-bye.
Thank you. Bye.